In this video, just as we did last lesson for the confidence intervals, we will entertain the far more realistic case of hypothesis testing for the population mean with the population standard deviation sigma unknown. We call this hypothesis testing the one-sample t-test. As we saw last lesson, the only practical difference is that we will have to deal with a distribution that, although still symmetric and bell-shaped, is no longer normal, but follows instead the student's t-distribution, and which depends upon the sample's degrees of freedom. Everything else will flow exactly as described in the scenario considered when the population standard deviation was known. So, let's go back to the fish in the lake example, this time with the condition that sigma is unknown, and ask the question, has the diet increased the population mean weight of the fish in the lake? Again, the null hypothesis contains all the outcomes in which the population mean weight has not increased. So the inequality on the null hypothesis must read less than or equal to. Whereas the alternative hypothesis contains all the outcomes in which the population mean weight has increased. So the inequality on the alternative hypothesis must read greater than. Because we collected a random sample of 40 fish from the lake, the central limit theorem applies, and we can describe the sampling distribution for the population mean weight of the fish in the lake as a student's t-distribution centered around the null hypothesis of 3.5 pounds. And with the standard error of the sampling distribution, not the standard deviation, remember that we do not know sigma, which is equal to the sample standard deviation of 1.7 pounds, divided by the square root of the sample size of 40 fish. Now we can place the sample mean of 4 pounds on the sampling distribution and calculate the t-statistic, which turns out to be 1.860. Because we are testing for an increase of the population mean and the alternative hypothesis contains the greater than inequality, then we just need to calculate the area to the right of t equal to 1.860 to obtain the p-value. Because we have a student's t-distribution, we use the Excel formula t.dist, taking care of including the value of the test statistic as well as the degrees of freedom, which are n-1 or 39. The p-value is equal to 0.0352, and because it is lower than our pre-agreed upon significance level of 0.05, then we can reject the null hypothesis and state that we have enough evidence to conclude that the population mean weight of fish in the lake has increased. Now, I want to make sure you understand that the main reason why the conclusions for the one-sample t-test differ from the conclusions in the last video for the one-sample z-test had nothing to do with the fact we used a different distribution, but simply because we imagined that a sample standard deviation of 1.7 pounds was considerably lower than the population standard deviation of 2.5 pounds. Had we considered an example where the sample standard deviation was the same of the population standard deviation, or even larger for what it's worth, then the conclusion between the two testing methodologies would have been much more similar. However, it is important you understand the conditions that led to the choice of one test over the other one and apply it judiciously. We can also use the alternative approach of the critical score rather than the p-value in the case of when the population standard deviation sigma is unknown. Again, all we have to do is to swap the z-statistic with a t-statistic and make sure we calculate areas using the correct Excel formula. Because we are dealing with the right-tail test, the region corresponding to the significance level will be entirely on the right side of the student's t-distribution, which, in this example, we decided to be 0.05. Now, we can use the Excel formula t.inv rather than the formula norms.inv, as we did for the normal model, to calculate the t-critical, indicated with the symbol t** or t star. The complement to alpha is 95%, which you can plug into the t.inv formula together with the 39 degrees of freedom and obtain a t-critical value of 1.685. Because we know that the t-statistic in this example is 1.860, it turns out that the t-statistic is greater than the t-critical. Therefore, we can reject the null hypothesis and reach the same conclusion seen for the p-value approach. At the end of the last video, we considered a couple of applications of the formula for the test statistic. First, we used it to estimate the range of sample means for which we would fail to reject the null hypothesis, and then to estimate the minimum sample size requirement to have a reasonable shot at rejecting the null hypothesis. In the one-sample t-test scenario, in which the population standard deviation is not known, the first approach is not possible because we need sigma to estimate the range of sample means. However, we can still estimate the minimum sample size requirement. Let us begin with the test statistic formula for the one-sample t-test. At the numerator, we have the difference between the sample mean and the hypothesized population mean, whereas at the denominator, we have the standard error of the sampling distribution of the sample mean. When the population standard deviation is unknown, we can write the standard error of the sampling distribution as the ratio of the sample standard deviation divided by the square root of the sample size. We can now plug the expression for the standard error of the sampling distribution into the formula for the test statistic and obtain the following expression for the test statistic. Using the t-critical approach, we learned that for a two-tailed test, we reject the null hypothesis when the module of the test statistic is greater than or equal to the module of the critical score at a given significance level. If we plug in the formula above for the test statistic, we obtain the following inequality. Let us focus on the sample size n at the denominator and define as target sample size n asterisk the range of sample sizes at which we can reject the null hypothesis. If we now solve for the target sample size instead, we obtain the following inequality. However, because the critical score for a student's t-distribution depends upon the distribution's degrees of freedom, which are equal to the sample size minus 1, this inequality is in implicit form and cannot be easily solved. We could solve it iteratively, but it would just not be worth the effort. Therefore, as we did in the last series of videos on confidence intervals, let us approximate the t-critical score with a corresponding z-critical, which does not depend upon the sample size. Again, let us consider an example to the weight of the fish in the lake. As you may recollect, the hypothesized population mean weight of the fish in the lake is 3.5 pounds. Whereas we assume the sample statistics on mean weight and related standard deviation to be 4 pounds and 1.7 pounds, respectively. Also, let us keep the significance level alpha at 0.05, with an associated critical score of 1.96 for a two-tailed test. If you now plug the numbers into the inequality shown in the bottom left-hand side of the screen, we obtain a minimum sample size requirement of 45 fish in order to have a reasonable shot at rejecting the null hypothesis. You may recollect how a similar calculation in a previous video led to minimum sample size requirement of more than twice as many fish. This is not due to a difference between the distributions, but simply because in this numerical example, we set the sample standard deviation at a considerably lower value than we did for the population standard deviation for the example in the previous video.